Hello, welcome to the second part of lecture 2. This is going to be a very short video and we are going to talk about a lot of things today that we have kind of already covered in our last lectures. We are still making a video about it again because I feel that these are some of the most fundamental topics, fundamental concepts in linear algebra, and a very solid understanding is absolutely essential. So let's begin. Well, you can see a two-dimensional space here, right? A two-dimensional plane. And now we can see a vector. This vector is going from the origin towards the point here, the point that we generally express using the coordinates 4, 3. Now, we have expressed this as a vector here. So on the one hand, we have a magnitude that is facing towards a certain direction, this direction from here to here. And on the other hand, we have a pair of numbers which are basically the coordinate of that point that is expressing the same vector. Now, these are pretty high school stuff, pretty basic stuff, but I'm still repeating it because when you look at a coordinate in a two-dimensional or three-dimensional or even higher dimensional space, I really want you to think of the coordinate from the perspective of linear combination. So when you look at these numbers 4 and 3, I want you to look at them and think of them as some form of scaling factor. This 4 and this 3 are scaling something. Here we have two very special vectors, I hat, which is the unit vector along the x-axis, and we have j hat, the unit vector along the y-axis. When you are looking at 4, 3, I want you to think that the first number, the number that corresponds to the x-coordinate of that point, is actually scaling the I hat vector by a factor of 4, and the number 3 is scaling the j hat vector by a factor of 3. And when you add these two vectors, you end up with our original vector. So essentially, this is nothing but a linear combination. This is true for all vectors. It can be any point in the space, and that point will have some coordinate, and each coordinate actually will be some form of linear combination of these two vectors, the vector I hat and j hat. And that's why these two vectors combinedly has a special name. We call them the basis of the two-dimensional vector space. You might want to remember this term, vector space, because this is going to come up a lot in our future videos. Anyway, so back to basis. I hat and j hat together create a basis of the two-dimensional space. Now, you may have noticed I use the term a basis and not the basis, and that's because the basis for a space is not unique. We could have created a completely different basis for this two-dimensional plane. For example, let's take these two vectors. Like I hat and j hat, can we reach any point in the two-dimensional space using these two vectors? Well, if you recall from our last lecture, the answer is yes. Just like I hat and j hat, if we take various linear combinations of these two vectors, we can end up in any point of the two-dimensional space here, which means these two vectors create a basis which is as good as the basis of I hat and j hat. And from there comes the idea of an alternative coordinate system. Let's say we call these two vectors x hat and y hat. When we express the y vector here using I hat and j hat, we ended up with a certain linear combination, which ended up becoming the coordinate of that point. But similarly, we can reach at that point using x hat and y hat as well. Obviously, the scaling factor for x hat and y hat would be much different from the scaling factor of I hat and j hat, which means that point will have a completely different set of coordinates when we are using x hat and y hat than when we are using I hat and j hat. I am showing you this just so that you can appreciate the fact that every two-dimensional vector can be expressed using two numbers as their coordinates, but what those numbers are going to be solely depends on our choice of the basis vector. For this point, if we choose the vectors I hat and j hat, we will end up with the coordinate 10 and 2.5. And if we had chosen the vectors x hat and y hat, we would have ended up with a much different coordinate, which is 2.083 and minus 0.83. Now let's talk about some of the terminologies that we have been using. The span of a set of vectors basically means the entire space where you can reach using the vectors of that set. In our previous example, when we are taking I hat and j hat, by taking the linear combination of those two vectors, we could reach anywhere in the xy plane. That is why the span of those two vectors is the entire 2D space. Similarly, the span of x hat and y hat is also the entire two-dimensional space, because just like I hat and j hat, using x hat and y hat, we can also reach anywhere in that space. On the other hand, we have the basis of a space. The basis means the set of vectors, the vectors that we absolutely need to reach every point of that space. Look at this 2D space here. We have a single vector. What is going to be the span of this vector? Well, if we scale it, we can reach anywhere in this line. But as we have only one vector, we cannot go beyond this line. So the span of this one single vector is just the straight line that it is in. And the basis of that one single line is this one single vector. Now if we add a second vector, that vector might give us a new dimension. But if that vector falls within the span of the first vector, we are not going to get anything new, because again, taking the linear combination of these two vectors, this is giving us the same old straight line. But if the second vector would have been somewhere other than the span of the first vector, like this, we would have had the entire 2D space, because now the second vector is giving us the second dimension. Now let's talk about some important factors here. Let's say you have a set of n vectors. That means you have a set of vectors, and in that set there are n different vectors. Using those n vectors, the maximum dimension that you can span or you can cover is going to be n dimension. Say you have two vectors. Three things can happen. If both of those vectors are the zero vectors, which means 0, 0, then you cannot span anything but the point 0, 0. If you have two vectors that falls on top of each other, then you have a straight line which gives you one dimension. And if you have two vectors which are independent of each other, then you have a two-dimensional plane as their span. But that's the most you can do with those two vectors. By spanning two different vectors, you can never create a three-dimensional space. Another factor here, if you have more than two vectors, you may have 3 vectors, 4 vectors, or 1,000 vectors. But if all of those vectors are of 2 dimension, which means they only have 2 components, x and y, spanning those vectors will never give you the third dimension, because these vectors have no component for the z-axis. So it doesn't matter how many vectors you throw at it, you will never reach the third dimension. So what I'm basically saying is, if your vectors are of n components, the maximum dimension you can touch cannot be higher than n. These concepts are very important, but they are also very vast. And we are going to delve into these topics even deeper, but we are still creating this video so early because it will help you to at least have a top-level concept of vector spaces and their basis and span. That is it for today. In our next video, we are going to talk about linear transformation. Until then, goodbye and thank you.